Today we're going to be doing a lab on mirrors. So before we start with the experiments, let's just review some of the things from lecture that are going to be relevant for today's lab. So the first is, what does it mean when we refer to the focal length of a mirror? So this is going to be our mirror for the purposes of illustration. It's shaped like a section of a sphere. And what we have over here are a bunch of incoming rays. So these rays are all parallel to one another when they come in before hitting the mirror. If we want to know what happens to each one of these rays after reflecting off the mirror, we just need to remember that the angle of incidence equals the angle of reflection. So that's going to be true for this ray up here. That's how we can predict which way it will reflect. That's also going to be true for this ray right in the center. It's going to reflect straight back from where it came. And then this ray down here again is going to obey angle of incidence equals angle of reflection. And if we follow all of those reflected rays to see where they're going, we notice that they converge at a certain point. And that's called the focal point of our mirror. Okay, so if we want to understand a little bit more generally how a mirror will form images, we're going to need to look at the mirror equation. So there are three variables in this equation. The first is DO. That's our object distance. That's just how far away from the mirror are we going to place the object. DI, that's the image distance. How far away from the mirror does our image form? And then finally F, that's our focal length, the distance from the focal point of our mirror to the mirror itself. Okay, so we're going to actually put the mirror equation to the test in today's lab. We're actually going to look at how a mirror forms images, where they form, and does it actually fit this equation. And in doing so, we're also going to measure the focal length of that mirror. The last little bit here is the lateral magnification. So the lateral magnification of a mirror is just the ratio of the image height to the object height. So HI over HO. So how big is your image compared to the size of the original object? That ratio is called the lateral magnification. And what we learned in lecture is this ratio is the same as minus DI over DO. So the ratio of image to object height is the same as the ratio of image to object distance. Again, we're going to see if that's in fact how it works in the real world in this experiment. So that's it for the introduction. Let's get into the first experiment. All right, so here's the setup for the first experiment. We have a track and various optical components on the track. We start at the left side of the track. We have our light source. And this is the same light source that we've used in the past. There's a screen in front of the light source so we can make different shapes. For today's experiment, we're going to be using the letter L. So our object is the letter L. Okay, if we go to the far right side of the track, we have a concave mirror. And this mirror actually can be adjusted. You can rotate it in place like this to get the reflected image to go in any direction you want it to. And then if we look at the middle of our track here, we have a half screen. So there's a white screen on this side, but this side doesn't have anything, so light is free to pass through. So the idea is light is going to come from our source through this side. It's going to then reflect off of our screen, and then it's going to reflect, the image is going to reflect back onto this side, and we can project the image onto this side. So the way this is going to work is, if I want to find exactly where the image is forming, I just need to move this screen around until I see a very sharp and in focus image being projected onto the screen. Okay, so the first measurement for today that we need to make is, what is the height of our object, which is again this letter L. So we'll measure it directly using a ruler. And what we get is exactly 2.0 centimeters. So HO for the experiment is going to be 2.0 centimeters. Okay, so for the first trial of the experiment, what we're going to do is set the object distance to 50 centimeters. So that's the distance between our light source and our mirror. That's 50 centimeters. And what we want to do is find where the image forms. So the image is projected onto this half screen, as we said earlier. But what we need to do is move the screen so that we get a really sharp and in focus image. So this is going to take some trial and error, but one thing to notice is if I push the screen way too close to the mirror, we get a really blurry image, so that doesn't work. If I push it way too far away, again, I get a blurry image. It's somewhere in between where that sweet spot exists, where we can get a perfectly and sharply focused image. And so, looks like it's happening right around here. And so our image distance, which is the distance between the mirror and where the image forms, that is 33 centimeters. Okay, so the next thing we'll do is measure the height of that image. And I'm going to be using a tape measure here, just so I can get right up against the screen. And you might not be able to see this on the camera, but the image height that I'm getting for HI is 1.4 centimeters. Next trial, we're going to set DO to 55 centimeters. So that's, again, the distance between our light source and our mirror. And next, we're going to locate where the image forms. We just do this by moving the screen around until we see the sharpest focus. And so this looks like the correct position. DI is now 31.2 centimeters. Okay, so that's the distance between where the image forms and the mirror. DI is 31.2 centimeters in this case. And lastly, for this trial, we can measure HI directly using a tape measure. And what we're getting in this case is about 1.2 centimeters for HI. So 1.2 centimeters. So the rest of the experiment goes in pretty much the same way. What we're going to do is increase the object distance by 5 centimeters for each trial. We're going to locate where the image forms, and then we're going to measure the height of the image. So we'll continue doing this until we reach an object distance of 90 centimeters, at which point we'll stop. I'm not going to show you those trials on the video right here. Instead, I'll just flash those up on the screen. So here's the data. So in this next experiment, we're going to be looking at virtual images that are formed by mirrors. Now, broadly speaking, what we're doing is pretty similar to what we did before. We're going to be setting up a mirror and then putting an object some distance away from the mirror. And then we're going to try to see where the image is formed. But since now we're dealing with virtual images as opposed to real images, this is going to be a little bit more tricky. Because when you have a real image, you can simply put a screen up and project the image onto the screen. And then you can see where the image is formed. Virtual images don't work that way. Virtual images can't be projected onto a screen. So if we're going to locate where a virtual image forms, we're going to have to be a little bit more inventive, and the technique we're going to use is a little bit more tricky. So let me introduce you to something called parallax, because this is what we're going to use to locate where virtual images are formed. Parallax is something you've probably experienced in your life at some point, but you may not have really thought about it or put it into words before. So follow along with me. This is a really quick demonstration of parallax, what it means. So I want you to start by standing up and then putting your thumb in front of you like this. Okay, and then try to hold your thumb still as you do this. Next, I want you to just move your head back and forth like this. And while you're moving your head back and forth, try to focus on something that's way off in the distance. So try to focus on a distant object. Okay? So what you're going to notice, if you do this for a little bit, is that your thumb appears to move around a lot more in your field of view than the distant object you were focusing on. Okay? So in other words, when you change your perspective, you move your head back and forth, objects that are close to you move around a lot in your field of view. And then objects that are far away move around a lot less. Okay, that's the effect of parallax. Okay, so if we can understand what parallax is and that effect we just described, think about this. If far away objects move less in your field of view when you change your perspective, and close by objects move a lot more in your field of view, what if two objects are the same distance away? Okay, like take your two hands and put them the same distance away from your face and then move your head around. Well, each hand moves around the same amount in your field of view. Okay, so when you're looking at two objects that are equally far away, they move around the same amount as you change your perspective. That's how you can know they're the same distance away. That's what we're going to use to locate virtual images in this lab. All right, so this is the setup for this experiment. So notice that we've taken the light source off the track, and now we just have this half screen. This is actually going to be our object for this experiment. And then we have a mirror. This is a convex mirror. It's set up 30 centimeters away from the object, so that means DO, the distance between the object and the mirror, is 30 centimeters. And then the last thing that's on the track is another screen, but what really matters is this little index card that's poking out with a line there. This is what we're going to use as a reference for distance. In other words, wherever we put this screen, that's where our virtual image is going to be when we complete the procedure. So the reason, again, finding the image is a little tricky here is we're not going to have an image that we can project onto a screen because this is a diverging mirror, right? It doesn't create real images. It creates virtual images. And the virtual image created by this mirror is always going to be behind the mirror over here somewhere. Okay? So we're going to try to look by eye where the virtual image is forming, and we're going to try to put this index card, or the screen with the index card on it, at that location, and therefore we can find out where the virtual image is forming. Okay, so if we go over here now and just sort of look into that mirror, so let me kind of point this out. This is the object. You see that line where the half screen is. You can see an image of that. In other words, you can see the half screen through the mirror right there. And that image is forming, again, somewhere behind the mirror. But if I use parallax, as we explained earlier, I can locate where that virtual image is. Because if I put that index card at just the right distance, when I move my head back and forth like this, the image I see in the mirror and that index card will move around the same amount. So let's say I don't place the index card at the right place, and maybe it's the index card is too far away, it's too far back. Okay, then when I do this, when I move my head back and forth, I'm going to notice that the image I see in the mirror is moving around more than the index card in my field of view. So what if I put the index card too close? Okay, then when I do this, I'm going to notice that the index card is moving around more in my field of view when I move my head around. But if I place it at just the right distance, okay, if I place the index card at just the right distance, then when I move my head back and forth, I'll see that the image in the mirror and the index card are moving around the same amount. Okay? That's how I know I've located where the virtual image is. And then, if I want to measure DI, once I've put this at the exact right spot, I can measure it straight off the track. Okay, so that's how we do this experiment. I'm not going to try to collect the data for this experiment because it's very hard to film that whole procedure. So instead, I'm just going to flash the data up on the screen. So that's it for the lab. You've seen both of the experiments and you have all the data you need to go and do your analysis now. So as usual, just follow along with the worksheet that I gave you. and that will explain the steps you need to take to carry out your analysis. There are two big results you're going to get from that. In the first experiment, you're going to measure the focal length of the mirror that was used, and I'm going to give you the manufacturer's accepted value for that focal length, so you should find very close agreement with that. And same thing goes for the second experiment. We'll have a focal length for that mirror as well based on the data we collected. Again, you should find very close agreement with the manufacturer's accepted value for that as well. So that's it. I'll see you in the next lab video. So take care. See you later.